Today we are starting chapter 5 integration. The title of this lesson is the architecture of accumulation. Before we think about integration as a formula, I want you to think about it as an idea. Integration is the mathematics of accumulation. It helps us answer questions like how much distance has been traveled, how much area has been covered, how much quantity has been collected over time. In earlier topics, especially derivatives, we studied change. A derivative tells us how fast something is changing at a particular moment. For example, if we know the position of a car, the derivative tells us its velocity. But integration asks the reverse question. If we know the velocity, can we recover the total distance traveled? This is why integration is so important. It connects small pieces into a whole. It takes many tiny changes and combines them into one total amount. On this slide, you can see a visual movement from discrete mathematics to continuous calculus. The bar-like blocks represent small separate pieces. The smooth curve represents a continuous process. Integration is the bridge between these two ideas. It begins with adding many small parts, and then it develops into a powerful method for studying continuous change. So in simple words, integration means accumulation. It is the process of adding infinitely many small quantities to find a total. Now let us begin with a real situation. Imagine an ice boat moving across the surface. We know its velocity. In the graph on the left, velocity is shown on the vertical axis and time is shown on the horizontal axis. The velocity function is written as v of t equals k times t. In spoken form, this means velocity at time t is equal to a constant k multiplied by time t. This tells us how fast the ice boat is moving at each moment. But our question is different. We want to know the total distance traveled. Distance is not shown directly in the velocity graph. So how can we find it? The key idea is this. Distance comes from accumulating velocity over time. If velocity tells us how much distance is covered per unit time, then multiplying velocity by a small amount of time gives us a small piece of distance. For example, if an object moves at 10 meters per second for 2 seconds, it travels 20 meters. That is velocity multiplied by time. But in real situations, velocity may not stay constant. It can increase, decrease, or change continuously. So instead of using one rectangle, we divide the time interval into many tiny time parts. For each small time part, we calculate a small distance. Then we add all those small distances together. Graphically, this total distance is represented by the area under the velocity curve. Therefore, the main message of this slide is to determine distance from velocity, we calculate the area under the curve. This is the starting point of integration. Now we move to the first method of understanding integration, slicing the area. Suppose we have a curve and we want to find the area under the curve from a starting point A to an ending point B. At first, this may look difficult because the top boundary is curved, not straight. So we use a practical approximation. We divide the interval from A to B into several small subintervals. Each subinterval has a small width called delta x. In spoken form, delta x means a small change in x. For each small interval, we draw a rectangle. The width of the rectangle is delta x. The height is determined by the function value at some selected point inside that interval. This selected point may be the left endpoint, the right endpoint, or another point inside the interval. The area of one rectangle is height times width. In this case, the height is the function value and the width is delta x. So each rectangle gives us a small approximate area. Then we add the areas of all rectangles together. The large summation symbol means we are adding many terms. In spoken form, we say the sum from I equals 1 to n of the function value at the selected x point multiplied by delta x. This is called a Riemann sum. The important idea is simple. We are approximating a curved area by using many rectangles. If we use only a few rectangles, the approximation may be rough. But if we use more and more rectangles, the approximation becomes better. Integration begins from this idea of slicing, estimating, and adding. This slide shows two common ways to estimate area using rectangles. On the left side, we see the left endpoint approximation. This means we choose the height of each rectangle using the function value at the left side of each subinterval. If the curve is increasing, then the left endpoint is usually lower than most of the curve over that interval. Because of this, the left endpoint method tends to underestimate the area. On the right side, we see the right endpoint approximation. In this method, we choose the height of each rectangle using the function value at the right side of each subinterval. If the curve is increasing, then the right endpoint is usually higher than most of the curve over that interval. So the right endpoint method tends to overestimate the area. In spoken form, the left endpoint sum can be described as add the function values at the left endpoints, each multiplied by delta x. The right endpoint sum can be described as add the function values at the right endpoints, each multiplied by delta x. The important message is that both methods are approximations. When the number of rectangles is small, the error can be large. One method may give a value that is too small, and the other may give a value that is too large. But the solution is not simply choosing the left endpoint or the right endpoint. The real solution is to make the rectangles thinner and thinner. When the rectangles become extremely thin, the approximation becomes extremely accurate. This idea prepares us for the exact definition of the definite integral. Now we reach one of the central ideas of integration, the limit process. On this slide, we see the rectangles becoming thinner and thinner. At first, there are only a few wide rectangles. The approximation is rough. Some parts are above the curve and some parts are below the curve. Then the number of rectangles increases. The width of each rectangle becomes smaller. The rectangle approximation begins to follow the curve more closely. Finally, in the ideal mathematical sense, we let the number of rectangles approach infinity. This means we imagine infinitely many rectangles, each with an extremely tiny width. In spoken form, the expression shown on the slide means take the limit as n approaches infinity of the sum from I equals 1 to n of the function value at the selected point, multiplied by delta x. This is the formal idea behind a definite integral. When becomes very large, delta x becomes very small. The jagged rectangle approximation becomes the exact area under the curve. So integration is not just normal addition. It is a special kind of continuous addition. We are adding infinitely many tiny pieces. Each piece is almost zero in width, but together they form a real measurable area. This is why integration is powerful. It allows us to calculate exact areas under curves, even when the shape is not simple. This slide explains the structure of a definite integral. The long stretch symbol at the beginning is the integral sign. Historically, it came from an elongated letter S because integration is related to summation. It represents continuous summation. Next, we have the lower and upper limits of integration. The lower limit is the starting value of x. The upper limit is the ending value of x. These two numbers tell us the interval over which we are accumulating area. Inside the integral, we have the function. This is called the integrand. The integrand tells us the height of the curve at each x value. At the end, we have dx. In spoken form, we say with respect to x. Conceptually, dx represents an infinitesimally small width of each slice. So when we read a definite integral out, we can say the integral from a to b of f of x with respect to x. Its meaning is accumulate the values of f of x from x equals a to x equals b. A definite integral gives a specific number. That number may represent area, distance, accumulated change, total mass, total work, or many other quantities depending on the context. This is different from an indefinite integral. A definite integral has limits and gives a number. An indefinite integral does not have limits and gives a family of functions. So the definite integral is a tool for finding a total amount over a specific interval. Now let us use integration for another important concept, average value. We already know how to find the average of separate numbers. For example, if we have 6 test scores, we add all 6 scores and divide by 6. That gives us the average score. But what if we do not have separate numbers? What if we have a continuous function? For example, temperature changing throughout a day, speed changing during a trip, or heart rate changing during exercise. In that case, we cannot simply add a few values unless we are only approximating. Instead, integration gives us the continuous average. The idea is shown visually on the slide. On the left, we have a curve function. The area under the curve represents the total accumulated value. On the right, this uneven shape is transformed into a rectangle with the same total area. The height of that rectangle is the average value of the function. In spoken form, the formula says the average value of a function over the interval from a to b is equal to 1 divided by b minus a, multiplied by the interval from a to b of f of x with respect to x. In simple language, we first find the total area under the function. Then we divide by the length of the interval. So the average value is not just a random middle point. It is the constant height that would produce the same total area over the same interval. This is very useful in science, engineering, economics, biomechanics, and data analysis whenever we need the average behavior of a changing quantity. This slide introduces one of the greatest discoveries in mathematics, the fundamental theorem of calculus. For many years, mathematicians studied area using limits of sums. That method is correct, but it can be very time consuming. Imagine trying to calculate exact area by always using infinitely many rectangles. It is conceptually clear but practically difficult. Then Newton and Leibniz discovered a powerful shortcut. They showed that differentiation and integration are deeply connected. Part 1 of the Fundamental Theorem of Calculus says something like this in spoken form. If we define a function by accumulating the area under another function from a fixed starting point to x, then the derivative of that accumulated area function is the original function. In simple words, a function defined by an integral becomes an antiderivative. Part 2 is often called the evaluation theorem. In spoken form, it says the integral from a to b of f of x with respect to x is equal to capital F of b minus capital F of a, where capital F is an antiderivative of f. This is very important. It means we do not always need to calculate infinite rectangles directly. If we can find an antiderivative, then we can evaluate the definite integral by subtracting its values at the boundaries. So the exact area under a curve can be found by using antiderivatives. This theorem is the bridge between differential calculus and integral calculus. This slide shows the relationship between differentiation and integration as a continuous loop. On one side, we have capital F of x. This can represent an original function such as position, accumulated distance, or total quantity. When we differentiate capital F of x, we get lowercase f of x. This derivative represents the rate of change. For example, if capital F of x represents position, then lowercase f of x represents velocity. Now we go in the opposite direction. If we integrate lowercase f of x, we can rebuild capital F of x. In other words, integration accumulates the rate of change and reconstructs the original quantity. This is why the slide says that differentiation and integration are mathematical undo buttons for each other. Differentiation breaks a function down to find how fast it changes. Integration accumulates the rate of change to recover the total. For students, this is a very important conceptual point. Derivatives and integrals are not separate topics. They are two sides of the same mathematical system. When we know the total function, we can differentiate to find the rate. When we know the rate, we can integrate to find the accumulated total. This loop is used everywhere: physics, engineering, economics, machine learning, motion analysis, and many real world systems involving change over time. Now, let us return to the iceboat example. Earlier, we knew the velocity of the iceboat, but we wanted to know the distance traveled. This slide shows how integration solves that problem. The top graph shows velocity as a function of time. The bottom graph shows accumulated distance as a function of time. When the iceboat moves with different velocities over time, the distance does not increase at a constant rate. It changes according to the velocity. The fundamental theorem of calculus tells us that if we integrate velocity over a time interval, we get net change in position or distance depending on the context. In spoken form, the expression on the slide says the integral from t1 to t2 of v of t with respect to t is equal to s of t2 minus s of t1. This means accumulated velocity over time gives the change in position from the starting time to the ending time. Here, v of t means velocity at time t. The function s of t represents position or accumulated distance. So if we integrate velocity from time 1 to time t2, we find how much the position changes during that interval. The key sentence is the definite integral of a rate of change gives the total net change. This idea is extremely useful. If we know speed, we can find distance. If we know flow rate, we can find total volume. If we know growth rate, we can find total growth. If we know force over distance, we can find work. Integration converts rates into totals. This slide compares derivative rules with integration rules. On the left, we see prior knowledge from derivatives. For example, the power rule for derivatives says that when we differentiate x raised to a power, we bring the power down and reduce the exponent by 1. In spoken form, the derivative of x to the power n is n times x to the power n minus 1. On the right side, we see the reverse power rule for integration. Since integration reverses differentiation, we do the opposite operation. We increase the exponent by 1 and then divide by the new exponent. Because this is an indefinite integral, we also add the constant of integration called c. So in spoken form, the integral of x to the power n with respect to x is x to the power n plus 1 divided by n plus 1 plus c, as long as n is not equal to negative 1. The slide also compares the chain rule with integration by substitution. The chain rule is used when we differentiate a composite function. Integration by substitution reverses that idea. When we see a function inside another function and we also see its derivative nearby, substitution can simplify the integral. The main point is this: every differentiation rule has a corresponding integration idea. To solve complex integrals, we often think of derivatives in reverse. So, integration is not just memorizing formulas, it is recognizing patterns and reversing the logic of differentiation. Now we focus on substitution, also called U-substitution. Look at the example on the slide. We have an integral involving 6x multiplied by an expression inside parentheses. The expression inside parentheses is 3x squared plus 4, and the whole expression is raised to the fourth power. This looks complicated at first, but we notice something important. Inside the parentheses, the inner function is 3x squared plus 4. Its derivative is 6x, and 6x is already present outside the parentheses. This is the signal that substitution may work. So we let u represent the inner function. In spoken form, we say let u equal 3x squared plus 4. Then the derivative of u with respect to x is 6x. That means du corresponds to 6x dx. Now the original integral becomes much simpler. Instead of writing the full expression again and again, we rewrite it as the integral of u to the fourth power with respect to u. This is much easier to integrate. The main message is substitution is a visual task. The integrand often tells us what to do. We look for an inner function and its derivative. If both appear together, we can substitute. So U-substitution is a method for simplifying integrands by replacing a complicated inner expression with a single variable. This slide gives us a 5-step process for U-substitution. Step 1 is identify. We choose the inner function and call it U. Usually this is a function inside parentheses, under a root, inside a power, or inside another function. Step 2 is differentiate. After choosing u, we find du. In spoken form, we find the derivative of u with respect to x and then express it in differential form. Step 3 is translate. We replace the inner function with u and we replace the derivative part with du. The goal is to remove all x terms from the integral. Step 4 is evaluate. Now we integrate the simpler function with respect to u. Step 5 is revert. After integrating, we replace u with the original expression in x. Let us say this in a simple classroom way. First, find the inside function. Second, differentiate it. Third, rewrite the integral using u and du. Fourth, integrate. Fifth, return to x. This cycle is very useful because it gives students a clear process. Many integration problems become easier when we follow this structure. But remember, substitution works best when the derivative of the inner function is already present in the integral or differs only by a constant factor. So when you see a function multiplied by something that looks like its derivative, think about U-substitution. Until now, many examples have involved powers of x, but integration also includes other important functions such as exponential functions, logarithmic functions, and inverse trigonometric functions. The first category is exponential functions. The special function e to the power x has a unique property. Its derivative is itself and its integral is also itself. So in spoken form, the integral of e to the power x with respect to x is e to the power x plus c. The second category is logarithmic functions. There is one important exception to the power rule. The reverse power rule does not work when the exponent is -1. That means the integral of 1 divided by x is not found using the normal power rule. Instead, it becomes the natural logarithm of the absolute value of x plus c. In spoken form, the integral of 1 over x with respect to x is the natural log of the absolute value of x plus c. The third category is inverse trigonometric functions. These often appear when we have denominators involving roots and squares. For example, expressions involving 1 minus x squared or a squared plus x squared can lead to inverse sine or inverse tangent. The important idea is pattern recognition. Different functions require different integration tools. A polynomial may use the power rule. A function multiplied by its derivative may use substitution. A fraction with x in the denominator may lead to logarithm. Certain square root patterns may lead to inverse trigonometric functions. So as we learn integration, we are also learning how to recognize mathematical shapes. This final slide summarizes the integration toolbox. The first visual trigger is a base variable raised to a constant power. For example, x squared, x cubed, or the square root of x. In this case, the category is the power rule. The action is add 1 to the exponent and divide by the new exponent. The second trigger is a function multiplied by its own derivative. This usually suggests substitution. The action is set the inner function equal to u and replace the derivative part with du. The third trigger is a fraction with x to the first power in the denominator, especially 1 divided by x. This suggests logarithmic integration. The action is integrate to the natural logarithm of the absolute value of x. The fourth trigger is a denominator formatted with square patterns such as a squared plus x squared or the square root over squared minus x squared. These patterns may suggest inverse trigonometric functions such as inverse tangent or inverse sine. This matrix is very helpful for students because integration can feel confusing at first. Many students ask, which method should I use? The answer depends on the pattern. So when solving an integral, do not start by memorizing blindly. First, observe the structure. Ask yourself, is it a power? Is there an inner function and its derivative? Is there a 1 over x pattern? Is there a square root or inverse trigonometric pattern? Integration is like choosing the correct tool from a toolbox. If we recognize the pattern, the method becomes much clearer. To conclude this lesson, integration is the mathematics of accumulation. It began with estimating area using rectangles. Then we used limits to make the approximation exact. The definite integral gives total accumulation over an interval. The fundamental theorem of calculus connects integration with differentiation. Finally, integration techniques such as the power rule, substitution, logarithmic integration, and inverse trigonometric patterns help us solve real problems. So, whenever you see integration, remember the big idea. We are adding many small pieces to understand the whole